Hello friends, welcome to Pensimtech Private Limited. So today we are going to see a very nice case study related to aerospace. Coming to the next slide. So this is a hypothesis of a study in which we are going to see how Airbus wing, if we are keeping that wing moving at the aircraft is moving at a highest speed, that is Mach number. What is Mach number? Velocity of aircraft divided by velocity of sound. So aircraft is moving at a speed or Mach number 0.85, that is in stratosphere. Okay. And okay, so let me tell something about this model. So Airbus A350 900. So 350 means it can carry 350 passengers. So large number of passengers. So it is very big model. The interesting point of this case study is the aircraft is at 25 km moving at its top speed with Mach number 0.89, and idea is to see the pressure and Mach number distribution, and the hardware used for this is only very nominal hardware, that is very low end configuration, you can say 16 GB RAM, 4 cores only, and for such a big model we simulated with this hardware. So for it can be used for study purpose, etc. Before moving to the next slide, I just want to say that okay, we have to see what are the different layers of atmosphere. So as I told that okay, we are moving in stratosphere, but what is before stratosphere, what is after stratosphere? So let's see. So that you can see this left hand side picture, just one second. So this picture, so here what we are seeing it here. So the first layer is troposphere, and after that stratosphere, and after that mesosphere, then thermosphere, then it is going merging into the space, that is exosphere. Okay, now this you can see the variation of different things. So how the temperature is varying in the troposphere. So in troposphere generally temperature decreasing up to stratosphere, and after that it will be constant, and then it will again increasing, and like that when it is merging to the space then it is increasing further. So that is for temperature. So similarly pressure. So as we are moving ahead, so what is sea level? Sea level means 0 meter, means you can say surface of the sea as a reference. So once we are moving up from the sea level towards the atmosphere and till 16 kilometer, it's around troposphere, and uh, during that phase once you are moving, your pressure will also decrease. Okay, so like that only. So that is why the idea is to see okay, one hypothetical situation, what will happen when our aircraft of Airbus carrying 350 passengers at its top speed in stratosphere. Generally why they are moving in stratosphere, because the in means the gust load etc are constant. That is calm layer, basically the layer are full of peace. Even eagles also flying uh, on that layer itself. So that means you can say that is a calm layer. That is why aircrafts are flying in that stratosphere. Okay. Now you can see there are some equations we derived here for troposphere. So this is ideal gas equation, rho equal to P by RT. And if you are substituting this T in terms of T naught 1 plus Kz, K is lapse rate. Okay, so lapse rate has some value, and we have to put that value. So after that is constant value. So that means once you are substituting this P in terms of rho by RT, so you will get like this type of equation. Sorry, rho. If you are substituting rho in terms of P, so you will get this type of equation. So dP by P, rho by RT naught, integration of with respect to datum we are integrating. Okay, so finally after the integration you will get logarithm P2 by P1 equal to minus Z R T naught K, and these all values are known. So what are the variables? P is the variable and Z is the variable. Okay, So you can get easily now the value of P at in troposphere. And okay, how you will calculate for stratosphere? So in the similar way, this is the equation for pressure for stratosphere, and you know rho equal to P by RT. As I told, stratosphere has constant temperature from 16 to 25. So simply you can substitute that value P of the troposphere and T of the troposphere, and you can get the value at 25 kilometer. Okay, so for your convenience, I already put that value here in my subsequent slide. So next go to subsequent slide. Next slide. So yeah, at 25 kilometer, the condition of atmosphere is this. So P equal to 2067 Pascal. Density is this. And you can see this is the view of the aircraft, and we have only considered this wing. And this area is very concern area. So if your flow is abrupt in this area, your aircraft will fluctuate, it will maneuver, so it will be in risk. So but we are seeing it here, there is no circulation, so consequently there is no induced drag as well. So what is induced drag? So in this area, due to delta P, induced drag is coming. Okay, here this area interference drag is coming. So that means interfering with different wing is interfering with different components of the aircraft. That is why this drag is called interference drag. I have not mentioned here, but please note it down. Okay. So this is the thing where everywhere you are seeing the flow is correct, right? So there is no abrupt recirculation, etc. So because of that, we can say this diagram is perfect, and this uh, this wing is also perfect. So design is also perfect, and that is why all the things. Okay, I think thank you very so thank you very much for. You can contact us for any type of simulation or any type of case study. So this is our number. So please contact us, and do some like, subscribe our channel. You can get lots of case study, you can get training, you can get even jobs also. So thank you very much.